This is the Honors Math 2 Unit 5 review. Number 1, what is the sum of the interior angle measures of an octagon? First of all, octagon means you have 8 sides. And to find the sum of the interior angles, what we're going to do is use the formula 180 times the number of sides minus 2, so 8 minus 2, which is 180 times 6, which is 1080 degrees. Number 2, what is the sum of the exterior angles in a convex 20-sided polygon? If you're looking at any convex polygon, doesn't matter how many sides, and you're adding up the sum of the exterior angles, that sum will always be 360 degrees. Number 3, the measure of an exterior angle of a regular polygon is 18 degrees. Find the measure of an interior angle, and then find the number of sides the polygon has. So, if you have a polygon, we're not sure how many sides. Okay, it's a regular polygon. Regular polygon means all the sides are the same length, and all the interior angles are the same angle. And we have an exterior angle at 18 degrees. Also means that all the exterior angles are 18 degrees. So if I want to find a measure of an interior angle, you can see in my drawing here the exterior angle is 18, the interior angle's what's left of a linear pair, and so we're going to find out, well, 18 degrees plus what is 180 degrees. So we subtract 18 and we get 162 degrees. So that's the measure of an interior angle. And then we want to find out how many sides there are. Well, remember, the sum of the exterior angles is 360 degrees. So what we can do here is say the number of sides is equal to, well, how many 18 degrees can we get in 360 degrees? So 360 divided by 18, and this is 20. So really 18 degrees is the measure of an exterior angle. All exterior angles, the sum of all of them is 360. So we know there's 20 exterior angles. But the number of exterior angles is the same as the number of sides. And it's the same as the number of interior angles. So 20 is the number of sides. 162 degrees is the measure of each interior angle. On number 4, we have a 5-sided figure, a pentagon. It's not regular because we have different angles we're looking at here, but we want to find the measure of angle x. So if we add them all up, 100 plus 100 plus 124 plus 118 plus x, it should equal the sum of the interior angles of a 5-sided polygon, and which is 180 times the number of sides minus 2. So we have an equation here in which we can solve for x. So when we add up 100 plus 100 plus 124 plus 118, we get 442 plus x is equal to 180 times 3, which is 540. Subtract 442 from 540, and we get 98 is x. Number 5, the sum of the interior angle measures of a polygon is 1980. How many sides does the polygon have? So if n is our number of sides, we have 180 times n minus 2. That's the formula for the sum of the interior angle measures, is equal to 1980. And then we're going to solve for n. I'm going to first divide by 180. And so n minus 2 is 1980 divided by 180, which is 11. And then if you have n minus 2 is 11, you add 2 to both sides and you get n is 13. So we have 13 sides. Number 6, find the value of j in the following parallelogram. So in one of the properties of a parallelogram is that the diagonals bisect each other, and or they cut each other in half. So this 4j minus 19 is equal to 2j plus 3, since the diagonals in a parallelogram bisect each other. So we can solve this, subtract 2j from both sides, add 19 to both sides, and divide by 2, and you get j is 11. Number 7, find the value of b. So looking at the picture, we see that the top and bottom are parallel to each other. Also the left and the right are parallel to each other. So this is a parallelogram. And another property in a parallelogram is that opposite sides are congruent. So we can say that b plus 14.5 is equal to 20.5, since opposite sides are congruent in parallelograms. And so if we subtract 14.5 from 20.5, we end up with b is 6. Number 8, find the value of s in the parallelogram below. So here, the top and the bottom segments are parallel, and so we're looking at same side interior angles. And if you remember, same side interior angles are supplementary. So we can take 8s plus 5 and add that to 3s plus 10, and we get 180 degrees. Since adjacent angles are supplementary, in parallelograms. So 8s plus 3s is 11s. 5 plus 10 is 15. Subtract 180 by 15, and you get 165. And divide 165 by 11, and you get s is 15. Number 9, we're asked to find the measures of the numbered angles in the following rhombus. So we know that angle 1 is 90 degrees. Since the diagonals of a rhombus are perpendicular, we know that angle 4 is congruent to angle 25 because the rhombus is a parallelogram, and those are alternate interior angles. So angle 4 is 25 degrees, since the rhombus is a parallelogram, and alternate interior angles are congruent. So we have angle 1 and 4 taken care of. We also know that angle 2 and angle 3 are congruent for the same reasons. That the measure of angle 2 is equal to the measure of angle 3. If we look at the bottom half of the rhombus here, notice it's an isosceles triangle because those two lengths are the same, and so both the base angles are going to be 25 degrees, and so we can find this third angle by 25 plus 25 plus x is 180, because the sum of the three angles in a triangle add up to 180. Subtract 50 from both sides and you get x is 130. And angle 2 is half of that, because the diagonal of a rhombus bisects the angles, and so so the measure of angle 2 and the measure of angle 3 is going to be 130 divided by 2, which is 65 degrees. And we used a few things. We used the idea of base angles of an isosceles triangle, are congruent. We use the sum of interior angles of a triangle equal 180 degrees, and we use that the diagonals of a rhombus bisect the angles. Number 10, solve for x in the following rectangle. So in a rectangle, well, in any the rectangle is a parallelogram, and we know the diagonals bisect each other. So those two lengths are the same. But we also have in a rectangle that the diagonals are congruent to each other. So actually we get all four halves equal to each other. So that makes the triangle I'm outlining isosceles, and so the base angles are congruent. So we can set 6x plus 3 equal to 5x plus 10, since we use two things, the diagonals of a parallelogram bisect each other, and the diagonals of a rectangle are congruent. And then the isosceles triangle theorem. So then we can go ahead and solve this. Subtract 5x, subtract 3, and we get x is 7. We're to classify each quadrilateral by its most specific name. So what we're noticing in 11, on the first one, I'm going to call it part A, is for sure it's a parallelogram, because opposite sides are parallel, and that's the definition of a parallelogram. But we also have a diagonal that is bisecting the angles. So in this one, obviously we have congruent angles there. If I draw my other diagonal though, is there anything that tells us that that diagonal bisects opposite angles? And we know that, that these two angles are the same. And we know that these two angles are the same. Obviously, if we knew both diagonals bisected both angles, we can get to a rhombus. But in this case, because we only have one, I don't see a way to show that it's a rhombus. So parallelogram seems the best and most specific name for this quadrilateral. Okay, the next one. Obviously it's a parallelogram because opposite sides are parallel. And there's no additional information given to us. We have the two diagonals drawn, but it doesn't tell us anything about how long they are, or nothing else is given to us. So the best we can say is that this is a parallelogram. I'll call that part B. Next one, part C. Here we have a parallelogram, and the diagonals are perpendicular to each other. And so, if we look at two triangles next to each other, I'll outline the two I'm looking at. Okay, we know they share a side, and we know that the two bases are congruent because the diagonals bisect each other in a parallelogram, and so we can see those two triangles are congruent by side angle side. So that that lets me know that these are congruent. And well, in a parallelogram, opposite sides are congruent, so that tells us all four sides are congruent. So now we have a rhombus. There's nothing that tells us that it's got four right angles on the edges, so it's not necessarily going to be a square. So rhombus is as good as we can get here. on, we'll call it part D, NP is congruent to OQ. Alright, so the diagonals are congruent. And they bisect each other. So all four pieces are the same length. So this is made up of four isosceles triangles. So I know that the two base angles using the isosceles triangle theorem are congruent in this bottom triangle. And then because the top and bottom sides are parallel, you can use alternate interior angles to get those are also the same as well. In a similar argument, not necessarily the same angle, but the opposite triangles here have similar angle sizes. So let's call this angle 1. All four of these are angle 1. Well, let's do x. Angle x. And the other one's going to be y. So if I have 4x plus 4y, that's the total of all four angles. And we know that with any four-sided shape, the sum of the interior angles is 180 times the number of sides minus 2, or 360 in this case. So 4x plus 4y is 360. I'm going to factor out a 4. I get 4 times x plus y is 360. Divide by 4 and you get x plus y is 90. Notice back in our picture here that each corner is made, the angle for each corner is x plus y. So all four corners are 90 degrees. And so we know this is a rectangle. There's not enough information to say it's a square, but we can get to a rectangle, and that's how. This next one, definitely a rectangle just by looking at it. We got a square here. Let me label these. So we did D, so this is E, F, call this G. And G, all four sides are the same, so that's a rhombus. Don't have to work as hard for these. On H, here we have a few things happening. Okay, so the top and bottom sides are parallel, and they're the same length. And there's a right angle here. Okay, well, if you have parallel lines, and so here's my parallel lines, and here's your transversal, in same side interior angles add up to 180 degrees, so that means this is 90 degrees. Let's see what else we can get from this. Now let me draw a diagonal. And again, because we have parallel lines or segments, these two angles are congruent because they're alternate interior angles. And they see it as two triangles, the triangle on top, triangle on the bottom. They share a side, and they're congruent by side, angle, side. So now we can get that the left and right side are congruent because corresponding parts of congruent triangles are congruent. We also get that this has got to be 90 degrees because it corresponds with the 90 degrees in the bottom triangle. And then if I erase the diagonal, I can argue, again, because the top left is 90 degrees, the bottom left has to be 90 degrees because same side interior, add up to 180. So we now have a rectangle. A little bit of work to get that one. Next one is a rhombus. Let's call this J. So here we have opposite sides are congruent. If I draw a diagonal and the two triangles share this side, and so they're congruent by side, side, side. So we have these two angles congruent because corresponding parts of congruent triangles are congruent, which tells us the top side is parallel to the bottom side by using the converse of the alternate interior angle theorem. Also, we have this angle is congruent to this angle, giving us these two sides parallel, again converse to the alternate interior angle theorem, so this is a parallelogram. Next one we have top and bottom parallel. So this is also a right angle because same side interior are supplementary. If I draw a diagonal, cut it into two triangles, we have alternate interior angles congruent here. Share a side. So they're congruent by we don't have congruence yet here because side angle is not going to work for us. What we do know though, I'll come back to this, well, change colors on here. So if we call this angle over here angle X, and this whole angle here angle Y. So on this one, no matter how you try it, there's no way to show that it's a parallelogram. One reason is this could be an isosceles trapezoid. So this could be a trapezoid, except for the fact that they give us this right angle. So I think some of these problems you got to think about a little bit. And I think we can come up with an argument that's going to work here. So let me put a little more information on here, or just more labels. This is K. We're going to call this A, B, C, and D. And so we don't know that AD and BC are parallel yet. I want to show that they are. Okay. So what I'm going to do is I'm going to say, okay, let's come up with another segment. And it's going to look a little funny here. But say they weren't parallel. Okay, so if AD and BC are not parallel, then there is another segment, say I'll put a point E here, where AE would be parallel to BC. Now it looks a little funny. Well, if that's the case, and actually I'll make it more extreme so we can see something here. Definitely does not look parallel. Okay. And we don't believe it is. But let's say these two are parallel. So then we'd have a parallelogram. EC is parallel to AB, AE is parallel to BC, and so we have opposite sides congruent. So this would be the AE would be the same length as BC, because we know that's true in a parallelogram. But then look at triangle ADE, right? We'd have, it's isosceles, so we'd have base angles congruent. Well, angle D is 90 degrees, so that means this would be 90 degrees. And do you see where we're running into a contradiction? This can't happen. And so, because all three angles in a triangle have to add up to 180, and we already have two angles adding up to 180. And so what I'm trying to show you is, this is what we call proof by contradiction, that we're assuming, we started by assuming AD was not parallel to BC, and that ran into a contradiction. That means AD is parallel to BC. So it's kind of a roundabout proof here, but we came up with the proof to show that AD is parallel to BC. And so we get a parallelogram. That is not an easy one to show why. It's kind of evident to look at, but to come up with a good reason why, we came up with one, but it's not a quick and easy one. This next one, opposite sides are parallel and opposite sides are congruent. This is a rhombus. This is L. M. We have all sides the same length, so it's definitely a rhombus, but we have one corner is 90 degrees, and because all sides are parallel, corresponding adjacent angles are all add up to 180, so that gives us 4 right angles. So this is a square. N. We have a parallelogram, and we have again, we're going to get 90 degrees on all 4 corners for the same reason. So this is a rectangle. O, we have all 4 sides the same length, and so this is a rhombus. Number 12, classify each quadrilateral by its most specific name. So in A we have a parallelogram. So I'm going to draw that. Parallelogram. Has perpendicular diagonals. And angle measures of 45, 45, 135, 135. So 45, 45, 135, 135. So if we go back up into the 11 part C, notice we had perpendicular diagonals, and we were able to show it was a rhombus. So our choice here is a rhombus or a square. We know this is not a square because the angles are not all 90 degrees, and so A is a rhombus. Part B, we have a parallelogram and it has perpendicular and congruent diagonals. So we know it's a rhombus. because of what we said in A. And then congruent diagonals, we looked at one of those in part D and came up with the argument that it's a rectangle. So it's a rhombus and it's a rectangle. So the only thing that's a rhombus and a rectangle is a square. So square is our answer. That's the most specific name. A parallelogram has, part C, a parallelogram has perpendicular diagonals, so it's a rectangle, and angle measures are all, perpendicular diagonals, so it's a rhombus, and angle measures are all 90, so it's a rectangle, so rhombus and a rectangle give us this square again. A parallelogram has congruent diagonals. So if they just have congruent diagonals, that's a rectangle, as we mentioned before. True or false? All kites are quadrilaterals. That is true by definition. A kite has 4 sides. A kite is a parallelogram. That is false. Just by the nature, in the definition, a kite has two adjacent sides that are congruent, 2 pairs of adjacent sides that are congruent. So but they're different lengths. So opposite sides are not congruent, and in a parallelogram you have opposite sides that are congruent. So that alone will tell us it's false. Part C, a kite can have congruent diagonals. So consider the case where we get congruent diagonals, something like this. Say both were length of 1, and they didn't bisect each other. Then you're going to get a kite shape. Okay, these cross at 90-degree angles, so all these are right triangles. This one's going to be bisected, but the other one will not be. And I think you can put some numbers to this. Say each of them were a length of 10. So this is 7 and 3, 5 and 5, and the top 2 triangles will have the same hypotenuse, which will be shorter than the bottom 2 triangles. You'll have a kite, and you have congruent diagonals. So this is true. D, both diagonals of a kite bisect the angles at the vertices. And that's going to be false. It is true for one of the diagonals, but not the other. And it should be obvious that these are not going to be bisected, and you can prove that right here. I'm not going to, but this is false. E, rhombuses have 4 congruent sides. That's true. That's the definition of a rhombus. F, rectangles have 4 congruent angles. That's true. That's the definition of a rectangle. The diagonals of a rectangle bisect the opposite angles. And that's false if you kind of extend, so make that your rectangle. You can see that, okay, yeah, that angle is not being bisected. It happens when you have a square, but not in every case, so that's false. And the diagonals of a rhombus are always congruent. Again, that's not true. If you have a kind of a squished rhombus, you can see that one diagonal is going to be a lot shorter than the other. But again, a square is a rhombus, so if you were looking at a square, that would be true. 14. we're looking to find the value of x. So here we are looking at a trapezoid. We have a mid-segment because we have a segment connected to two midpoints of the sides of the trapezoid. And from the mid-segment theorem, we can say that 2 times the middle length is equal to the sum of the top length plus the bottom length. And that's by the trapezoid mid-segment theorem. And so we have an algebraic equation we can solve. So this is 2x is equal to 3x minus 20. Subtract 3x and you get negative x is equal to negative 20. And multiply both sides by negative 1 to get x is 20. On 15 we have another it looks like a trapezoid, except for the fact that a trapezoid we have to have two sides parallel, and it's not stating that. Let's say it is a trapezoid. Let's add this in here. Let's make this a trapezoid, and then what we call this is an isosceles trapezoid. What we know about isosceles trapezoids is that the base angles are congruent. So both of these angles are congruent to each other. Also, both of these angles are congruent. And so we can say that 3n is equal to 117, since the base angles of a trapezoid are congruent. And dividing by 3, we get n is 39. (16) Find the measures of the numbered angles in the rhombus below. So we're going to have to use a few properties here. First of all, the diagonals in a rhombus are perpendicular. Because we have all four sides the same length. And so that tells us angle 2, the measure of angle 2 is 90 degrees, since the diagonals of a rhombus are perpendicular. Okay, also, if we look at the left side of this rhombus, that triangle, it's an isosceles triangle, so we know the base angles are the same. And we also know the diagonals bisect the angles, so this is also 52. So if we call this x and x, we have x plus 52 plus 52 is 180, because the sum of all the angles in a triangle add up to 180. So that's 2x plus 104 is 180, or 2x equals, subtract a 104 from 180 and you get 76. and divide 76 by 2 and get 38. And so that's the measure of angle 1. So measure of angle 1 is 38, and what we used is the isosceles triangle theorem, stating that the base angles are congruent, and we also used that diagonals of a rhombus bisect the angles. Then we can say that the measure of angle 3 is equal to the measure of angle 1, which is 38, because they're alternate interior angles with parallel segments. This side is parallel to this side, giving us alternate interior angles are congruent. And now we just need angle 4. So if we look at the bottom right triangle, the one I'm highlighting, that is a right triangle. And so the measure of angle 4 plus 90 plus the measure of angle 3, which is 38, is equal to 180, because the sum of all angles inside of a triangle is 180. 90 plus 38 90 plus 38 is 128. Subtract 128 and you get the measure of angle 4 is 52 degrees. We're going to write the coordinates of J, K, M, and L. What's given is this is an isosceles trapezoid. So there's those are congruent. These are parallel. With the base centered at the origin, which is 0, 0. And bases are 2b, 4a, and 2b. And the height is c. So I'm going to let the bottom base length be 4a, the top length be 2 times b, and the height be c. So that would make, well, if you cut 4a in half, you're going to have to go 2a to the right. So the L would be at, going to the right 2a, and height 0. So that's the coordinate of L. M, you'd go left 2a, so negative 2a, height 0, so negative 2a, 0. For K, you're going to go to the right b and up c. And J, you're going to go to the left b and up c. And there are your coordinates. Number 18. Write the coordinates of W, X, Z, and Y. We have a parallelogram with the height M and point Z, distance J from the origin. Okay, so Z is the distance J from the origin, and the height of this parallelogram is M. Okay, so the point Z we know is J, comma 0. Is there anything else we have here? Parallelogram with height M. Well, W we know is going to be 0M. Okay, and from there from there we have a choice. We get to pick what distance we want z to y to be and w to x to be. We'll let, so this is our choice. Let the distance zy equal k. So if I'm going to go k, so then y would be j plus k, comma 0. And opposite sides are congruent, so x would be 0 plus k, m. So we got to pick that distance. It didn't have to be k, it just had to be the same distance and you would have had it. Okay, number 19. 3 vertices of a parallelogram are given, and I'm going to go ahead and sketch those. So I'm going to call 0, 0 point A, 2, 5 will be my point B, and 5, negative 2 will be my point C. So A is right here, 2, 5, right here, 5, negative 2, right here. And so what's given here is we have this right here. And I'm just going to take note of a few things. First of all, the slope of AB using rise over run is 5 over 2. And the slope of AC, rise over run, is negative 2 over 5. Okay. First of all, notice they're opposite reciprocals, so they're perpendicular to each other. And I'll mention that a little bit later too, so I can put a 90-degree angle there. But we're looking for a fourth point, D, that will complete this parallelogram. So I want my side to be parallel to side AB. Since the slope of AB is 5 over 2, from C I'm going to go up 5, right 2, and that puts us at 7, 3. And I'm thinking that's going to be the point that's going to complete it. We need to do some confirming here just to make sure we're thinking right, but that's the idea. So let's show that this is a parallelogram now. So the slope of BD, using the slope formula, y value minus y value, so 2 minus 7 over 5 minus 3, is going to give us negative 5 . Sorry, I did this wrong. Let me fix that. I said it right, but wrote it wrong. So y minus y, so that would be 5 minus 2, 5 minus 3, and then over 2 minus 7, which is negative 2, which is positive 2, over negative 5, or negative 2/5. Okay, and notice BD and AC have the same slope, so they're parallel to each other. And then the slope, one more here, what are we missing? CD, slope of CD. Using our slope formula, y value minus y value over x minus x is 5 over 2. And so from that information we can get AB is parallel to CD because they have the same slope, and also AC is parallel to BD because they have the same slope. And so this is going to give us that AB CD is in fact a parallelogram. Also, by looking at those slopes, we see that AB is perpendicular to AC, and AB is perpendicular to BD. BD is perpendicular to DC, and DC is perpendicular to AC. And this is because the slopes are opposite reciprocals. Which is telling us that all these are 90 degrees, and so ABCD is a rectangle. We still don't have that it's a square. We're getting closer. Let's look at the length of AC. Well, we know first of all that AC is congruent to BD, and AB is congruent to CD because that's a property of a parallelogram. Opposite sides of a parallelogram are congruent. So we're going to call back on that in a second. So it's enough to just find two lengths. Let's show that AB is congruent to AC by finding the length. So AB, using the distance formula, is going to be 5 minus 0 squared plus 2 minus 0 squared, which is the square root of 25, plus 4, which is the square root of 29. So that's the square root of 29. Also, because it's a parallelogram, we know that CD is also the square root of 29. And now let's go after AC. AC is the square root of 5 minus 0 squared plus negative 2 minus 0 squared, which is the square root of 25 plus 4, which is the square root of 29. And again, opposite sides are congruent, and so now we see all four side lengths are the same, and so that's evidence that we have a square. So ABCD, well, is a rhombus by definition. And since ABCD is a rectangle and a rhombus, we got that ABCD is a square. Okay, on to number 20. So here we're given TY XW as a parallelogram, and we're going to do a two-column proof here. So statement reason. And so we'd like to show that it's a rhombus. So the givens, T, Y, X, W is a parallelogram. And TP congruent to TZ. WZ is perpendicular to TY. These should all have segments above them. And YP is perpendicular to TW. So let's mark what we have here. So TP is congruent to TZ. This is perpendicular here. This is perpendicular here. And our reason is given. Good first reason. And so what I would like to do here is to show that triangle TZW is congruent to triangle TPY. So I think that's going to lead us to helping, just be a very big help in this solving this. First of all, notice they share this angle at point T. So, and it's already given that, as we said, TZ and TP are congruent. So we have two of the smaller sides of those triangles congruent. So we're going to say angle ZTP is congruent to angle PTY. Or PT, I should say ZTW, because those are the parts that belong to that triangle. So let me follow that. It's the same angle. And PTY. And because it's the same angle that they're sharing, that we're using the reflexive property. Something is equal to itself. Third, something that is in the givens, I'm just going to state it here, angle TZW is congruent to angle TPY. And the reason is, well, from the givens, they're both 90 degrees, they're perpendicular. So using the definition of perpendicular, we get that both angles equal 90 degrees, and we're using the definition of congruent angles to say that they're congruent. And so we're referring to part 1. So now we have enough information here to prove that the triangles TZW and TPY are congruent by angle-side angle congruence. So that first part we accomplished. So now that we've established that the two triangles are congruent, we can say that these two sides that I'm highlighting, TY and TW, are congruent because those are sides of those triangles. And so I'm going to continue my proof over here. Statement, reason, on to statement 5, that TW is congruent to TY, and our reason is corresponding parts of congruent triangles are congruent. So to prove something is a rhombus, we got to show that all four sides are congruent. We've shown that the full side TY is congruent to the full side TW. Now the last real move here is to say that, well, TW is congruent to what's across from it, YX, and TY is congruent to what's across from it at WX. And the reason is opposite sides of parallelograms are congruent. So now we see all four sides are congruent, and so we're just going to end our statement here saying that TYXW is in fact a rhombus. And we're referring or relying on the definition of a rhombus. And looking at 5 and 6 to help us get there. And 5, we looked at 4 to help us get there. On to our last problem, number 21. Given KRPM is a parallelogram, and angle JRK, right here, is congruent to angle PMO, right here, prove that JROM is a parallelogram. So, a statement, reason table again. Givens are KRPM is a parallelogram, and angle JRK is congruent to angle PMO. So reason is it is given to us. So here we would like to show, and I'm going to highlight it. So, well, actually, so we're given KRPM. So this part right here is in fact a parallelogram, and we want to show that this part is a parallelogram that I'm highlighting in green. And to show something's a parallelogram, we need to show that opposite sides are parallel. Well, first of all, we can say that JM is parallel to RO. And the reason is that JM is an extension of KM, part of the same extended line, and we could say that RO is an extension of RP, and KM is parallel to RP since KRPM is a parallelogram. Okay, so that part we're getting from our givens. So the rest of the work here is to show that JR, so we have this, is to show that JR is parallel to MO. To do that, what I'm going to focus on trying is to show that the left triangle is congruent to the right triangle. So we know that RK and PM are congruent. And the reason is opposite sides of parallelograms are congruent. And so we have side angle, and we just need another piece. Well, we can state that angle J and angle O are congruent because opposite angles in a parallelogram are congruent. And so what we can say now is that angle, these two angles here, so angle JKR is congruent to angle KMP. And the reason is corresponding angles are congruent with parallel lines. Okay, and then we could say that angle KM P, so KMP is congruent to angle KRP, and the reason is opposite angles in a parallelogram are congruent. And then we could say angle KRP is congruent to angle MPO, by corresponding angles are congruent with parallel lines. And all of this to say that angle JKR is congruent to angle MPO. By substitution. And we're looking at 4, 5, and 6 here to help us with that. So all this now to finally get to our triangles are congruent. Haven't proven the parallelogram yet, but we're hoping this part will help us. So triangle JRK is congruent to OPM. And we're using angle side angle congruence. Alright, so now that the triangles are congruent, what can we do? Well, we can say that angle J is congruent to angle O, since corresponding parts of congruent triangles are congruent. We can say that angle O and angle JMO are supplementary, since RP KM is a parallelogram in our given. So JM is parallel to RO, and same side interior angles are supplementary. And then finish this off just about. Oops, that should be 11. Angle J and angle JMO are supplementary. Using substitution. Using 9 and 10. Running out of space here, I'm going to move over here. So statement 12. So angle, well, so JR, there's what we want, is parallel to MO. And our reason is if we have same side interior supplementary, then we get that they're parallel. One of the findings with parallel lines. So now from statement 12 and from statement 2, we've finally proven it. JROM is in fact a parallelogram. Using the definition of a parallelogram, and referring to statement 2 and statement 12. Yikes, that's a big one.